Hello everyone. In the last part, we have learned about methods that deal with missing data by disregarding individuals with missing observations. In this part, we will learn about single imputation. And the idea is that rather than discarding individuals with missing observations, another possibility is to fill in or to impute the missing values. And basically, what these approaches do is that they generate a single replacement value for each missing observation. And because we are only generating a single replacement value, we use the designation of single imputation, and this is in contrast to multiple imputation where several copies of the dataset are created, and then for each copy of the dataset that we have created we impute the missing values with plausible estimates. And single imputation, by just replacing each missing value with a generated plausible value, leads to a single completed data set, completed in the sense that we no longer have missing values, we have replaced them by our generated estimate. And then with this completed data set we can perform our analysis of interest, with our analysis of interest being the analysis that we would have conducted in case we had no missing values. We will cover several single imputation methods, and basically we will learn about unconditional mean imputation. Then we will learn about conditional mean imputation or regression imputation, which is an improvement of unconditional mean imputation. Then we will learn about stochastic regression imputation, which again is an improvement of conditional mean imputation. And unrelated, we will learn about odd-deck imputation. And lastly, and also unrelated, we will learn about a method called last observation carried forward, and this is a method that is particular to longitudinal or time series data. And a disclaimer: whenever a single imputation strategy is used, we must be aware that the standard errors of the estimates, or the variance of our estimates, will tend to be too low. And why? Well, the intuition behind this fact is that we have considerable uncertainty about the values that are missing, but by choosing a single imputation, we are kind of pretending that we know the true value, the value that we are imputing with certainty. And obviously this is not the case. If we knew the true value with certainty, the value would not be missing, and somehow we are overestimating the information available in the completed data set. And this is why multiple imputation is preferred over single imputation. And we will learn about multiple imputation later in the course, but nevertheless, single imputation is still paid attention in the literature. And additionally, some of the single imputation methods, especially stochastic regression imputation and odd-deck imputation, they are a step in the right direction, and they also form the basis of multiple imputation techniques, so they deserve our attention. And to fix ideas or to be concrete, we will be using a toy dataset. This is an hypothetical dataset, but we will be illustrating at least the first three single imputation methods: mean imputation, regression imputation, and stochastic regression imputation, with this small bivariate dataset. So basically, we have two variables: pain severity and depression, and this is about 20 chronic patients enrolled in a pain management program. And basically, we know that patients with mid pain are more likely to refuse the depression measure. And for pain severity, we have observations on all 20 individuals, and for depressions, 5 individuals are missing their depression score. And we will look at the different single imputation methods, at least at the first three single imputation methods, by using this small data set as a concrete example. And okay, let us start with mean imputation. Mean imputation is also known in the literature as unconditional mean imputation or marginal mean imputation. And basically, for the variable that has missing values, we will replace the missing value by the overall mean of the observed values for that variable. And this is for the case of continuous variables. In case the variable is categorical, the mean might not make sense, and we should use the mode of that variable to replace the missing value. So for our bivariate data set with pain and depression scores, we know that the depression score variable has missing values for 5 individuals, and if we compute the mean of that variable for the 15 individuals that have observed measurements, we obtain that the mean is 15, and so we replace the missing values on the depression score variable by 15. And we know that arithmetically the estimate of the mean after mean imputation must always be the same as the mean for the observed data, because we are just imputing the values with the mean for that variable, and so the mean remains the same after we do the imputation, because we are using the mean to impute the missing values. And I think it's intuitive to think that by imputing values at the center of the distribution, we will be reducing the variability of the data, right? In case the depression scores were observed for that 5 individuals, it's not possibly reasonable to think that their observed value would be exactly the mean of the variable, right? Some would be lower than the mean, some others could be above the mean, but exactly on the mean it's kind of unreasonable to think. And this way, the mean imputation attenuates the standard deviation of the variable with missing values. And for instance, in our running example, the standard deviation of the completed variable, of the completed depression score variable after we have performed mean imputation is 3.37, and the standard deviation of that same variable, but before performing the imputation, just by computing the standard deviation of the available 15 individuals, we would have obtained 3.93. And we know that we already have reasoning that imputing values with the mean of that variable will attenuate the standard deviation of that variable. And also, the mean imputation also attenuates not only the standard deviation, but the magnitudes of covariances and correlations between variables, right? And if we think about the covariance formula, we have computed some covariances, some sample covariances in the last video. And for instance, if I'm computing the covariance between the depression and the pain scores, call it Y1 and Y2, I know that the sample covariance, between Y1 and Y2 is 1 over n minus 1, right? This is the sample covariance expression, right? This expression here, but imagine that the depression score is represented by the variable Y2. For the individuals that we have imputed the data with the mean, we know that their observed value minus the mean of the variable will be 0, because we have imputed the value exactly with the mean. So the numerator will be, for those individuals with imputed values, will be contributing with a 0, and that's why we are attenuating the covariances. And also, if we look here at the scatter plot of the pain severity scores, again the depression scores, and the black dots are our observed data and the red dots are the imputed data. And we immediately see that they fall on the imputed values, they fall on a horizontal line, which implies that the correlation is 0 for the subset of individuals with imputed depression scores. And in fact, if we compute the correlation between the pain and depression variables for the observed data, so excluding the 5 individuals with missing values on the depression score, and we also exclude those for the pain score to compute the correlation. So basically doing a complete case analysis, we obtain that the correlation is 0.62 and the correlation for the observed data is 0.48. Of course, we should not just judge how good are our imputations or our estimates by looking at the observed data, because we know that unless it's missing completely at random, the observed data will not be a random sample or will not be a good representation of the completed data. But just to make the point clear that by using mean imputation, we are attenuating the covariances and the correlations and also the standard deviation of the variable with missing, or the variables with missing values. Okay, and okay, are there any good things about mean imputation? Yes, is a fast and a simple fix for the missing data problem. We just look at the variables with missing values and we impute the values on each variable with the mean of that variable. So it's easy, it's fast, but we have already seen that it will underestimate the variance, it will attenuate the correlations between variables, and it will bias any almost estimate other than the mean, and all these things even if the missing data mechanism is missing completely at random. And if data are not missing completely at random, we will also obtain biased estimates of the mean. So basically, if data are missing completely at random, which we know is a very strong assumption, but okay, assuming that data are missing completely at random, if we do mean imputation and then estimate the mean, then we do not have biased estimates, but we will have biased estimates of the variance, of the correlations, and of the covariances. And then if data are not missing completely at random, not only we have biased estimates of the standard errors of the correlations, but also about the means. So mean imputation is not really a recommended method, and in fact it has been suggested that mean imputation is possibly the worst missing data handling method available. And next week we will conduct a simulation study to look at to empirically look at some features or some properties, sorry, of the different missing data of the different single imputation methods that we will be learning, and we will see in fact that mean imputation is really bad. And quoting Julie Josse, a researcher that works on missing data methods, and that she will be giving a seminar in our seminar series on the 18th of November. So if you are interested, please join. And she basically said, and I'm quoting her here, that in case you have missing completely at random values, you might better go with a complete case analysis rather than with a mean imputation fix. And because basically of the things that we have just discussed, you have obtained biased estimates of basically any quantity that you will be interested about. And we know that complete case analysis under missing completely at random, you do not obtain unbiased estimates. You do not obtain biased estimates, sorry, they are unbiased, the estimates that you obtain, but you know that they are less efficient because the standard errors tend to be higher because we have a reduced sample size. So main points: mean imputation is a quick fix, but it's not a recommended method for deal with missing data in general or even in any particular situation. And okay, is there a way that we can somehow improve on mean imputation? Yes. Conditional mean imputation, also known in the literature as regression imputation, is an improvement on the mean imputation approach because it replaces each missing value with a predicted conditional mean from a regression equation. Basically, with mean imputation, we do not use the information from any other variable in our data set. But in conditional mean imputation, and that's why the method is called conditional mean imputation, we use information from the other variables. And to fix ideas here, we will be dealing with the situation where we have several variables, but only one variable has missing values. In the lectures of next week, we will see how to deal with the case where several variables might have missing values. But for now, we concentrate on the case where we have several variables, but only one variable is allowed to have missing values. And the idea behind this method is quite interesting. So basically, we are using information from the complete variables to fill in the incomplete variable. And because variables tend to be correlated, it makes sense to generate imputed values that somehow borrow information from the observed variables. And basically what we do is, and again, we are in the context where we only have one variable with missing values, so it's kind of a univariate pattern, or it's a univariate pattern for missing data, and we can rearrange our data set in a way that the first block corresponds to individuals with observed values for all variables, and the last block, or the second block, corresponds to individuals with which have missing values for the variable that is allowed to have missing values. And basically for our block of observed data, what we do is we use a regression model where the response of our regression model is the variable that contains missing values, and all the other variables act as covariates, okay? And we estimate the model from our observed data using the variable that is missing, or that has missing values, as our response, and the fully observed variables as covariate. And then in a second step, we use the estimated regression model, we estimate the regression coefficients, and then we predict the missing values based, because all the other variables, they have observed information, and we can predict our missing values from the regression model that we have fitted on the completed or on the observed data set. Okay, just to illustrate, for our bivariate data set, we have 20 individuals, 15 of them have available information on both the pain score and depression variables, and then 5 individuals have missing values for the depression score. So basically what we do is the following. For the 15 individuals with observed data on both variables, we fit the following regression model. Is this regression model here, where our response is the depression score, and then we do a simple linear regression model. In this case, we can do different things, but here let us use a simple linear regression model. So basically we have an intercept, and we have the pain score variable, the associated regression coefficient, and some random noise, and we assume that the errors are IID from a normal distribution with mean 0 and some constant variance sigma square. And remember that for these 15 individuals, I know the depression score and the pain score, so I can fit my model in the standard way, right? And then I obtained, once I have fitted my model, I obtain the estimates of beta 0 and of beta 1. And then for the 5 individuals that have missing observations, I can use my estimated beta 0, my estimated beta 1. I observe they have the depression score missing, but the pain score is observed. So I can just predict how using exactly this equation here. Beta 0 hat and beta 1 hat are obtained from the observed data from the regression model that I fit to the observed data, and then I use I use the estimates that I have obtained to predict the missing values. And for instance, to make things more concrete, for the 5 individuals that have missing values on the depression score, I know their pain score, right? So if I want to use this equation here to predict their corresponding depression score for the first individual, I just replace the pain score by 4 and I do this calculation here and I obtain the predicted depression score, and the same for all the other 4 individuals. Okay, and just to make an apart here, I'm using a simple linear regression model. If I had more variables with completed information, I would use a multiple linear regression models, but there are some assumptions here that they need to be satisfied. In particular, in this case, that the relationship between the depression and pain scores is linear, that the errors are independently and identically distributed, that they have a normal distributed, and that they are normally distributed, or they have a normal distribution, sorry, or they follow a normal distribution, and that the variance of the errors is constant. So the variance does not change with the covariates, or in this case with pain score. Okay, so there are 4 assumptions here. Independent errors follow a normal distribution with constant variance, so 2 assumptions, normal distribution and further constant variance, and the relationship between depression and pain scores is linear. We can then relax and note that this sometimes open the door to some confusions. This is not my model of interest, in the sense that possibly this would not have been the model that I would be interested in analyzing or in conducting in case my data set was completed. But this is just a step to complete my data set. So basically, I do not want to check, or I do not need to check whether pain score is a significant variable or not. I'm just using my observed variables to predict the variable with missing values. I have no scientific interest in this model, in this regression model. I just need that the assumptions are satisfied because I'm fitting the model, and if the relationship, for instance, is not linear and is quadratic, so the imputations, they don't have much value because they are not accurate. But just to make the point that this is not the model that we are interested in, this is just a model to impute the missing values. Then once we have our completed data set, we perform the analysis that we would have performed in case we had no missing values. Okay, just to make this point clear. And now if I look at the scatter plot, remember that for mean imputation, the imputed values, they fall on the horizontal line, and the depression score value was 15 for all imputed values. Here it's exactly the opposite. The predicted or the imputed values for the depression score, they fall on a line, they fall on the regression line. And remember that for mean imputation, the correlation between the correlation for the subset of individuals with imputed values were 0 because they fall on a horizontal line. And here is exactly the opposite, because they fall on a line with a non-zero slope. The correlation between this subset of points is 1. And by looking at this scatter plot, we can also immediately notice that the imputed values, they vary less than the observed values. So it's kind of unrealistically to think that in case we had no missing values, or in case we had observed the values with missing values, that they would fall exactly on a regression line, right? So it's not very realistic. So in this case, regression imputation, it has the potential to increase the correlations, right? Because the subset of imputed values, they have correlation of 1. And also the standard deviation is also attenuated, because it's not as bad as in mean imputation, but the imputed values, they also vary less than the values that we would have observed in case there were no missing values. Okay, and uh, in fact, if we compute the correlation for our completed depression score variable after performing regression imputation, we obtained 0.71, which is larger than 0.61, that is the correlation between the variables using a complete case analysis, okay, from the observed data. And as a consequence, regression imputation overestimates correlations even when data are missing completely at random, okay? So we can, even under missing at random, we can obtain unbiased estimates of some quantities, but in general, regression imputation also has this drawback. The imputed values, they don't show much variation, because they have they lie on a regression line, and also because of that the correlations are artificially increased. But I think we all agree that regression imputation is way better, or at least better than mean imputation. So if we can improve regression imputation, then it would be great, right? And what is the main drawback of regression imputation? Is that the imputed values, they fall on the regression line, and this attenuates the variability of the data and increases the correlation. So what about if you use those values, but then we add some noise? So we will introduce some dispersion. And this is exactly what stochastic regression imputation does. So the main idea is very similar. We, for the observed data, we fit a regression model, and it's exactly the regression model that we have used for regression imputation. We used as the response variable the variable that contains missing values, and all the other fully observed variables as covariates. Then we predict, using the fitted model, we predicted the values for those subjects that have missing observations. And then we have these predicted values. These are the same as for regression imputation, but we had some noise. And the noise that we add, is basically, this is what we had before, okay? And then I add some noise, this zeta, and this zeta follows a normal, here I forget to put, they are IID, from a normal distribution with mean 0, and sigma square, or sigma hat square, is the estimated residual variance that we can also obtain this value from our fitted regression model. So basically we are introducing noise in our predictions, and this somehow restores the lost variability that we had in regression imputation. And it has been shown that stochastic regression imputation provides unbiased parameter estimates of correlations of regression coefficients under a missing at random mechanism. So it's quite good. What is the main drawback of stochastic regression imputation? It's a good method, but it's still a single imputation method. So basically we are replacing the missing value with these predictions from the regression imputation that we add noise, but we are just replacing each missing value with one of such value. And so we know that any single imputation mechanism will underestimate the standard errors or the variances of our estimate. factors, and stochastic regression imputation as a single imputation method, it suffers from this drawback. But apart from this, is a very powerful method, and in fact stochastic regression imputation, it's on the basis of more advanced techniques, in fact of multiple imputation. We will learn multiple imputation, as I said several times already, later, and stochastic regression imputation forms the basis of one of the multiple imputation techniques that we will learn about. So a good thing about stochastic regression imputation is that it generates parameter estimates that are unbiased under a missing at random mechanism, and also missing completely at random. The only drawback is that it's a single imputation mechanism, so we know that we are underestimating the standard errors of our estimates. Okay, and again, if we look here at the scatter plot, it looks much more realistic. Note that I have fixed the seed, and somehow, because we are generating random numbers, right? So if you don't fix the seed, you will obtain a different plot, and that is okay. But because I have fixed the seed, note that the 4 values, they kind of still lie in a line, but this is completely by chance. If I have used other seeds, the values would have been different. And in fact, in the next video, we will be looking at R and how to generate these values, and we can play around and see that if we use a different seed, the values will be different. And okay, again, I will repeat myself, but here we are not performing any of the analysis of interest. We are just completing the data set, right? We are just generating imputations for the missing values. Then once we have the completed data set, we can do whatever we want or whatever we are interested in, okay? And yes, a point that I think I need to make about stochastic regression imputation, because we are adding a normal random noise, it might be that depending on the seed and on the residual variance, that for some cases we might obtain negative predicted values. And in this case, if I had obtained a negative predicted value for the depression score, this does not make any sense in practice. So I would be replacing the missing value with an unreasonable value. And what we could do is a kind of ad hoc but simply fix. I generate a new value, and if it's negative, I discard it, and if it's positive, I retain the value. Okay, but just to be aware that stochastic regression imputation can lead to implausible predictions, but we know how to fix it. Even if it's not the most practical thing, we know a way to fix it. Okay, so this is all about the 3 first missing data single imputation mechanisms for missing data. So we have seen mean imputation, lots of drawbacks. Then regression imputation is an improvement, and stochastic regression imputation is an improvement, and it's actually a very good method for dealing with missing data. It has its drawbacks because it's a single imputation mechanism, but it's good. So let's very quickly talk about hot-deck imputation. And hot-deck imputation has its roots in survey application. It was first developed having in mind survey applications, and basically it's a collection of techniques that impute the missing values with values from similar individuals in our data set. And this is in opposition to cold-deck methods, where the imputation, we are replacing the missing values with imputations that come from a previously collected data source. But for hot-deck imputation, we are using the data set that we have, and we will impute the missing values with values from similar, and we need to define how these similar individuals are found. And there are several modifications of the first proposed hot-deck imputation methods. It's a method that has been upgraded or improved, let's say, through the years. And yes, the basic idea is to impute missing values from other individuals. In its simplest version, and think about our running example, we have the the depression score variable that has missing values. And what we would do in the simplest version of the hot deck method is just to pick up randomly one of the individuals in our observed one of the 15 observed individuals and replace each of the missing values with different randomly selected individuals. So for the first individual with a missing value, I look for the other 15 individuals with observed values. I randomly pick up one and I replace the missing value with the value of that individual. Then I do the same for the second individual with a missing value. I look at the 15 with observed depression scores and I randomly pick up one and I replace, and I do that. And okay, here I'm not using any other information from, for instance, if I have a data set with more variables, and even here I'm not using any information about the pain score. Maybe I could look for individuals that are similar in their pain score variable with the individual that has missing values. And if I have more variables, I can look for similar, and I need to come up with a similarity measure. But for instance, I can look for individuals that are in the same age range, of the same gender, and with the belonging to the same race group. I can look at several other information that I might have available about the individual with missing values and form a group of similar individuals. And if those individuals, they have their observed value for the variable that has the missing values, and I then pick up randomly one of such individuals and I borrow their value, in this case of sync the depression measure, to replace the missing value. And the matching variables, they do not need to be categorical. I can use matching variables that are continuous, and in fact there is an extension to the nearest neighbor hot deck, but we will not look at it. So basically, hot deck imputation, it looks at similar individuals of those with missing values, and then it pick up a value from those. We call them the donors, and those which are similar, or sorry, who are similar to the individual with missing value on several other variables, they qualify as donors to donate their value on the variable that has missing values. Okay. And it has been shown that hot deck imputation, generally does not attenuate the variability of the imputed data to the same extent as other imputation methods, but it can produce substantially biased estimates of correlations and regression coefficients. And again, as any other single imputation method, it underestimates the standard errors, and there have been corrections have been proposed. But again, hot deck, we can also extend it to the case of multiple imputation, where we create several copies of the data set, and then we impute each copy of the data set using a hot deck procedure. So we look for similar individuals to the individual that has missing values, and we then use one of the values of those individuals to be to donate the value. Okay. And yeah, that's basically it about hot deck. And lastly, just to mention that it exists, we will not be looking at it. It's the last observation carried forward method. And this is, as I said in the beginning, very particular to longitudinal or time series data. And basically what we have is, on longitudinal data, we have several time points, right? And if I have a missing value for the last time point, say, I just impute this value with the value from the previous time point. So for instance, if I have, let's say, for some individual, we have measurements on week 1, week 2, week 3, and think of the individual 1, and it has an observed value for a given outcome of 20, 23, and then it has an NA, a not available. And so under last observation carried forward, we just use the value of week 2. So we would replace this NA with a 23. And imagine that we have an individual 2, which has 19, at 25, but this value is missing. Again, if I use last observation carried forward, we replace this NA with a 19. So basically that's it. It's kind of a crystal ball, right? We are using the information from the past to fill in or to replace the missing values, and it can produce biased estimates even when data are missing completely at random. It's kind of very used, this last observation carried forward in the medical sciences, but it's really not recommended. So I don't think there is much to recommend about the last observation carried forward. There might be very particular situations. For instance, if you don't expect the outcome to change a lot, maybe using last observation carried forward, it might be okay. But in general, I don't think it's reasonable to do this. And several researchers has shown that this technique should not be used by because of a variety of reasons. And that's it about single imputation. We have covered different methods to generate replacements for the missing values, and here we have just cared about completing the data set. Then we have done nothing more. Once we have our completed data set, we can do wherever it's of our interest. Okay. And I finish with a quotation from Dempster and Rubin from 1983. I think it's an interesting small reads or short reads, and that's it. We will have one more video about how to perform these imputations in R, how to produce the plots that I have shown, and some of the values using R. Okay, thank you.